Hello everyone, today we're presenting our weather forecasting project. Our main goal was to develop predictive models for weather and climate change in a given city. To do this, we initially started off forecasting the maximum temperature and precipitation in Boston using classification and regression models, guessing tomorrow's max temperature and precipitation using today's temperature and rain indicator. However, we soon discovered that these models were not performing great as they failed to account for a critical component, that is, seasonality. With our previous models, you can imagine if we were forced to extend our predictions from tomorrow's temperature and rain to next week's or next month's, they would become more and more divergent from the actual weather. If we can fit a part of our model to the seasonality itself to cancel it, we can fit the rest of our model to the remaining trend as we would normally do. So how did we account for seasonality? As we presented previously, we used a time series model, SERIMA, which stands for Seasonal Autoregressive Integrated Moving Average. After running training and testing our SERIMA model, we wanted to explore other models to improve our prediction accuracies. We created a neural network by adding seasonality factor with engineered features. Let's first take a look at our project's basic structure. We had previously been working with just a Boston weather dataset. Since our midterm report, we've extended our predictions to 5 other cities around the world, including Buenos Aires, Darwin, New York, Madrid, and Vladivostok. Let's take a look at our dataset and how we cleaned it. We got the maximum temperature data from 1970 to 2025 for our 6 cities, which we downloaded as a combined CSV file with specific station names for each city and the Tmax response variable. We picked these 6 cities based on availability of data in the year range. For all of the cities in our data set, we replaced the missing values using linear interpolation.
Before training and testing our neural network on our 6-city dataset, let's examine how we set up our neural network for a given dataset for a random city, like Miami. We start off by hypertuning our model to find the best combination of parameters such as hidden layers, alpha, learning rate, and we see for these combination of parameters which one gives us the best accuracy. Once we find the best parameters that give us the best accuracy, we are able to retrain on the entire dataset, and then we could forecast the weather for the next 20 years. In this graph, you can see that we forecasted the weather for the city of Miami from 2025 all the way up to 2045. Following the same procedure as before, we now want to run our model on the 6 different cities we mentioned earlier. So, we start off by hypertuning our parameters, and then running our model for each city, and evaluating on the separate test sets. Starting off with the Boston dataset, we got a mean average error of 7.2. For Buenos Aires, we got a mean average error of 5.3 Fahrenheit. For Darwin, we got a mean average error of 2.3 Fahrenheit. For New York, we got a mean average error of 5.9 Fahrenheit. For Madrid, we got a mean average error of 5.8. And lastly, for Vlad, we got a mean average error of 6.6 Fahrenheit. Overall, our model performed best for the city of Darwin, giving us a mean absolute error of 2.3 Fahrenheit, which means that on average, our model is off by around 2.3 Fahrenheit in terms of predicting the maximum temperatures. We think the reason our model performed best for the city of Darwin is because the dataset does not fluctuate as much as other datasets. As you can see, the range of the maximum temperatures is from 80 to 100, while other datasets have a larger range.
Let's wrap up this project a little bit. Back from the midterm, we were using SARMAX a lot. And as you can see in this plot here, it's doing pretty well, and we've also added on the neural network, which is also doing pretty well. It's a little smoother than SARMAX. So one issue we ran into with SARMAX was just time. It took about an hour to be running it when we were doing it in 5-day increments, so we only took 1 day per every 5 days. And scaling this to predict every single day would have taken on the order of maybe 5 to 10 hours. So switching to neural networks helped us reduce the speed. So going back to neural networks helped us fix this and go on the order of just a couple minutes to fit and forecast. In conclusion, we would recommend using neural networks for this problem, but with the caveat of if you have limited data, it could potentially be better to use SARMAX because the neural networks did not work very well when we had more limited data. Overall, this was a fun project, and it was really nice to be able to incorporate things that we learned in class in the continuation of our project. Thanks to the professor and the TAs for helping facilitate this, and thanks for watching. Bye-bye.